In today's video, we're going to look at how we can use the row operations we had studied previously to find the inverse of a matrix if it exists. Now, this is going to be another theory-heavy video, so there's going to be a lot of proofs in this video, but that is going to enable us to develop a much quicker way of finding a matrix inverse. An n by n elementary matrix of type 1, type 2, or type 3 is a matrix obtained from the identity matrix by performing a single elementary row operation of type 1, type 2, or type 3, respectively. In other words, type 1 elementary operation is swapping two rows. That'll produce an elementary matrix of type 1. Type 2 is multiplying a row by a non-zero constant. That results in an elementary matrix of type 2. And type 3 is multiplying a matrix by a non-zero constant. Multiplying a row by a non-zero constant and adding it to another row. And that results in an elementary matrix of type 3. Now, let A be an m by n matrix, and let an elementary row operation of type 1, 2, or 3 be performed on A to yield matrix B. Let E be the elementary matrix obtained from IM, the m by m identity matrix, by performing the same elementary row operation as was performed on A. Then B is equal to E times A. In other words, whenever you perform an elementary row operation on a matrix, you can represent that operation as a product of the corresponding elementary matrix times the original matrix. Now, if A and B are m by n matrices, then A is row equivalent to B if, and only if, there exist elementary matrices E1, E2, so on and so forth, up through EK, such that B is EK times EK minus 1, so on and so forth, times E2 times E1 times A. For the proof, what we will do first is assume that A is row equivalent to B. Right? If this is the case, then by definition, remember, the matrix B results from A by a sequence of elementary row operations. This implies there exists elementary matrices E1, E2, so on and so forth, up through EK, such that B is equal to EK times EK minus 1, so on and so forth, times E2 times E1 times A. Now, this comes straight from Theorem 1. Now, conversely, right? So in order to prove an if and only if, you must prove both directions. So start by assuming that A is row equivalent to B, and show that B has to be a product of elementary matrices and A. Now we have to assume that there are elementary matrices such that B is that product, and show that A is row equivalent to B. So if B is equal to EK times EK minus 1, so on and so forth, times E2 times E1 times A, where each of these E's, I'm going to write this way, where each E sub I is an elementary matrix, then B results from A by a sequence of elementary row operations. Now, again, that is from Theorem 1. This would then imply by definition that A is row equivalent to B. And that completes our proof. Now, an elementary matrix E is non-singular, and its inverse is an elementary matrix of the same type. Right? So theorem 3, this is saying that we can undo a row operation by another row operation of the same type. Lemma 1, a homogeneous system of M linear equations in N unknowns always has a non-trivial solution if M is less than N. In other words, if you have fewer linear equations than you have unknowns, then there's always a non-trivial solution. Right? So for the proof, I'm going to say let B be a matrix that is in REF, RREF even, that is row equivalent to the matrix A. Then what we notice is the homogeneous systems AX is equal to 0 and BX is equal to 0, right? So remember, all a homogeneous system is a system in which all of the constants are zeros. So these two systems are equivalent. Now let C be the augmented matrix be augmented with 0. Then obviously this means that C is in RREF. And we may ignore any row of C that consists entirely of zeros. Right? And this is because if we have a row in C entirely of zeros, then when you convert that to an equation, that means that's saying 0 is equal to 0, right? So it doesn't give us any pertinent information about the system. Right? Now, let rows 1, 2, up through R of C be the non-zero rows. And let the leading 1 in row I occur in column C sub I. So what we are doing is we are solving a system, a homogeneous system even, of our equations in n unknowns. I.e., or with r less than n. Right? So we have fewer equations than unknowns. In this case, we can solve for xci, xci minus, xc1, xc2, up through xcr in terms of the remaining n minus r unknowns. Right? So since the latter can take any real value, there are infinitely many solutions. To bx is equal to 0, which means that there exists a non-trivial solution. Since bx equals 0 and ax is equal to 0 are equivalent, we can therefore conclude that ax equals 0 has a non-trivial solution. That is exactly what we wanted to prove. So the proof is complete. Let A be an n by n matrix, and let the homogeneous system ax equals 0 have only the trivial solution. Then A is row equivalent to the identity matrix. In other words, if we have a system of n by n matrix, a system of n equations and n unknowns, and we have only trivial solution, then we know that A is going to row reduce to the identity matrix. So what we say is, let B be a matrix in RREF that is row equivalent to A. Right? Then the systems AX equals 0 and BX equals 0 are equivalent. Therefore, we know that bx equals 0 has only trivial solution. right? Because equivalent systems have identical solution sets. It is clear that if R is the number of rows of non-zero rows in B, then Bx equals 0 is equivalent to the homogeneous system whose coefficient matrix consists of the non-zero rows of B and is thus R by N. Now, since this last system is homogeneous, or since this last system is homogeneous and has only the trivial solution, R has to be greater than or equal to N by the previous lemma. Right, we just proved that. However, because B is R by N, we also must have that R is less than or equal to N. Right, because remember, the original matrix B was N by N. R represents the non-zero rows of B. Well, the most you can have is N, and if you start eliminating 0 rows, then you're going to get less than N. So we have R has to be greater than or equal to N. We also have that R has to be less than or equal to N. Therefore, R equals N, which means that B has no non-zero rows, which means that B has to row reduce to the identity matrix. And that completes the proof. Now, A is non-singular if and only if A is a product of elementary matrices. And this is another if and only if, which means we have two directions we have to prove. Let's start. If A is the product of elementary matrices E1, E2, up through EK, then A is equal to E1 times E2 times E sub K. Now remember, each elementary matrix is non-singular, and the product of non-singular matrices is also non-singular. Right? Therefore, A is non-singular. Oh, good. Now we have to do the converse. And so conversely, if A is non-singular, now we have to show that it is the product of elementary matrices. Well, we know then that AX equals 0 leads to A inverse times AX is equal to A inverse times 0. Right? Which means since A is non-singular, I sub n times x is equal to 0, right? Because anything times a 0 vector is still 0. And the identity matrix times any vector would be that vector. So we're left with x is equal to 0. Which means that AX equals 0 has only the trivial solution. Therefore, lemma 2 implies that A is row equivalent to IN, which means there exists elementary matrices E1, E2, so on and so forth through EK, such that I sub n equals EK times EK minus 1, so on and so forth, times E2 times E1 times A. Right? It then follows that A inverse is equal to this. Right? But remember, by properties of matrix multiplication and inverses, this is E1 inverse, E2 inverse, so on and so forth, EK minus 1 inverse times EK inverse. But the inverse of an elementary matrix is an elementary matrix. Specifically, of the same type. Therefore, we have now written A as the product of elementary matrices, which was what we desired, and so the proof is complete. A consequence of this is that A is non-singular if and only if A is row equivalent to IN. In other words, it's non-singular if and only if a row reduces to the identity matrix. First, if A is row equivalent to the identity matrix, then we can write the identity matrix as EK times EK minus 1, so on and so forth, times E2 times E1 times A, where each of the EI's is an elementary matrix. Right? Therefore, it follows that A is equal to E1 inverse times E2 inverse, so on and so forth, times EK minus 1 inverse times EK inverse. Right? Therefore, A is the product of elementary matrices, which means that A is non-singular by the theorem we just proved, Theorem 4. Conversely, if A is non-singular, then A is the product of elementary matrices that is, A is equal to E1 times E2, so on and so forth, times EK. Right, but A we can write as A times the identity matrix, which is E1 times E2, so on and so forth, EK times that identity matrix, which means that A is row equivalent to IN, which is what we wanted. And so the proof is complete. And so the homogeneous system of n linear equations in n unknowns, ax equals 0, has a non-trivial solution if and only if A is singular. Right, so if we take a look, lemma 2 and corollary 1 together will imply that if ax equals 0 has only trivial solution, then A is non-singular. Therefore, if A is singular, then ax equals 0 has a non-trivial solution. Conversely, consider ax equals 0 and let A be non-singular. Then, by the proof of Theorem 4, ax equals 0 has only the trivial solution. Therefore, if ax equals 0 has non-trivial solution, then A is singular. That is what we wanted, and so the proof is complete. What we have now done is shown that the following 5 statements are all equivalent, meaning if any one of these statements is true, the remaining 4 are also true. For any n by n matrix A, first, A is non-singular. Second, ax equals 0 has only the trivial solution. Third, A is row equivalent to In. Fourth, the linear system ax equals b has a unique solution for every n by 1 matrix B. And fifth, A is a product of elementary matrices. Now for the actual method. Right now, at the end of the proof of Theorem 4, recall that A was non-singular, and we could write it as a product of elementary matrices. Right, specifically E1 inverse, E2 inverse, so on and so forth, from which it would follow that A inverse is the inverse of that product, which is EK times EK minus 1, so on and so forth. This provides an algorithm for finding A inverse. What we do is perform elementary operations on A until we get In. The product of the elementary matrices, EK, EK minus 1, so on and so forth, E2, E1, would then give us A inverse. A convenient way of organizing the computing process is to write down the partitioned matrix A augmented with In. Then, if we take this product of elementary matrices times that augmented matrix, we would get the product times A augmented with just the product. Now the product times A is going to give us In, and then obviously this product is simply A inverse. In other words, what we do is augment the matrix we wish to find the inverse of with the appropriate sized identity matrix, put that matrix in RREF. The result will be the identity matrix augmented with the inverse of the matrix. This will only work if the inverse actually exists. We will consider what if the inverse doesn't exist in the next theorem. Theorem 6 states an n by n matrix A is singular if and only if A is row equivalent to a matrix B that has a row of zeros. Right, so first, let A be row equivalent to a matrix B that has a row of zeros. It follows that B is thus singular. The proof of this is left as an exercise. Now, B is equal to EK times EK minus 1, so on and so forth, times E2 times E1 times A, where each EI is an elementary matrix. Now, if A is non-singular, then B would be non-singular, which is a contradiction of the fact that B is singular. Therefore, we must have A is singular. Right? Now, conversely, if A is singular, then A is not row equivalent to IN. Therefore, A is row equivalent to a matrix B different from IN that is in RREF. Therefore, it follows that B must have at least one row of zeros. And that completes the proof. We will now go ahead and apply this method to find the inverse, if it exists, of these two matrices. And so matrix 1, matrix A, what we do is take the matrix, augment it with the appropriate size identity matrix, which in this case is 3 by 3. Now what we do is RREF this. Right? So the first step in the process will be multiply row 1 by -5, add it to row 3. The result is this. Next step. Actually, let's do 2 and 1. Multiply row 2 by 1/2. Multiply row 3 by -1/4. Now, let's take -3/2 row 3 and add it to row 2, and also take -1 row 3 and add it to row 1. And finally, take negative row 2 and add it to row 1. Right, so we now have the identity matrix on the left-hand side, which means that right-hand side is our A inverse. Right? And you can always verify this is indeed the correct inverse by simply multiplying it by A and verifying that you get the identity matrix. Now for matrix B, we once again take the matrix, which is 1, 2, -3, 1, -2, 1, 5, -2, -3, and augment it with the 3 by 3 identity matrix. First, let's do negative row 1 plus row 2, and then -5 times row 1 plus row 3. Make that look more like a 5, shall we? There we go. Now let's take -3 row 2, add it to row 3. And notice what we have. On the left-hand side, we have a row of zeros. Therefore, there is no B inverse. All right, so B is singular. One final property to look at. If A and B are n by n matrices such that A times B is In, then B times A is also In. In other words, if A and B are inverses, then the order in which you multiply them doesn't matter. You will get In either case. To prove this, let's suppose that A is singular. Then this means that A is row equivalent to a matrix, call it C, that has a row of zeros. Right. Now, we know that C is equal to EK times EK minus 1, so on and so forth, times E2, times E1 times A, where each of the EIs is an elementary matrix. Therefore, C times B is equal to EK times EK minus 1, so on and so forth, times E2 times E1 times A times B, which implies that AB is row equivalent to C times B. Since C times B is going to have a row of zeros, we conclude from Theorem 6 that A times B is singular. Which implies that A times B cannot equal IN. And this is because IN is an elementary matrix, and so is non-singular. I'm sorry, IN is not elementary matrix, but it is non-singular, which is a contradiction. Right, AB is supposed to equal IN, but we just said it's not. So our assumption that A is singular must be wrong. So therefore A is non-singular. Right, so A inverse must exist. Multiplying both sides of AB equals IN by A inverse on the left yields the following. We get A inverse times A times B is equal to A inverse times IN, which means that B is equal to A inverse. Since B is A inverse, we conclude that the proof is complete. That concludes our video on using row operations to find the inverse of a matrix. In the next video, we will be finishing our study of matrices and linear systems by looking at a different method of solving a system of linear equations using matrices by using what is known as the LU factorization of the matrix. So thanks everyone for watching. I hope you enjoyed, and I will see you all in the next video.